Welcome back to Basic Electronics. We now come to a very important and commonly used building block in electronics, that is an operational amplifier or op-amp in short. We will start with an introduction to op-amps and look at their advantages. We will then take a brief look at the internal circuit of one of the early op-amps, namely the 741. We will see the input-output relationship of an op-amp and identify the linear and saturation regions of operation. We will look at two approximations that we can make to analyze op-amp circuits when the op-amp is operating in the linear region. Okay, let us get started. We now talk about op-amps, and we will consider several circuits which use op-amps. Op-amp means operational amplifier, and it is a versatile building block that can be used for realizing several electronic circuits. And really, you cannot think of electronics without op-amps these days. It's extremely commonly used and very, very useful. The characteristics of an op-amp are nearly ideal, and we will take a look at what these are. And therefore, op-amp circuits can be expected to perform as per theoretical design in most cases. That's an advantage because we don't need to usually worry about second order effects. Amplifiers built with op-amps work with DC input voltages as well. Now, if you recall, the common emitter amplifier, for example, had a coupling capacitor to connect the input voltage to the amplifier. And if you apply an input voltage and input DC voltage, that coupling capacitor would obviously block the DC input voltage and it will not reach the amplifier. That is not the case with op-amp circuits. And amplifiers built with op-amps can also work with DC input voltages, and this makes them very useful in sensor applications. For example, you want to measure a temperature or a pressure, so there is a voltage which is proportional to the temperature, for example, that you want to measure, and that could well be a DC quantity or a very, very slowly varying quantity, because temperatures don't normally vary very rapidly. So this feature of op-amps is surely very useful. The user can generally carry out circuit design without thorough knowledge of the intricate details of an op-amp. So generally, we don't need to worry about what is inside an op-amp, and that makes the design process simple. And we will see several examples of that. Here is the internal circuit of the 741 op-amp, which is very commonly used and is also low cost. And in all likelihood, you will probably use these 741 op-amps in your electronics lab courses. What is the first impression of this circuit? That it is very, very complex. It is, but it's possible to analyze it stage by stage. So there is the first stage here, there is a current source which supplies the first stage, then there is a second stage, and there is an output stage, etc. And this analysis can be found in a few textbooks. A very nice systematic analysis of the 741 op-amp is indeed possible. For our purpose, we will not get into how each of these transistors works, what is its purpose, and so on. But we will look at this entire op-amp as a black box. And that is the nice thing about op-amp circuits. We usually don't need to worry about what goes inside. Let us look at the pins of this IC now. There are two inputs marked plus and minus here. This input is called the non-inverting input, and that is called the inverting input. That is the symbol of an op amp. So the non-inverting and inverting inputs are shown here. The output of the op amp is taken here, and that is shown here. So it's an amplifier. You apply a voltage between these two inputs, and the difference between these voltages gets amplified, and that appears at the output. In addition, we have this power supply nodes, VCC and minus VEE. VCC could be 10 volts and minus VEE could be minus 10 volts, for example. So they are complementary, and this VEE normally is treated as a positive number, so minus VEE is negative. And those power supply inputs are also shown here in this symbol as well. Note that there is no separate ground pin for this circuit, and we will comment on that in the next slide. In addition to these pins that we have already discussed, there are two more pins, these two, and they are meant for something called offset adjust, and we will look at this a little later. So altogether we have 1, 2, 3, 4, 5, 6, 7 pins for the op amp 741. Now the 741 comes as an 8-pin package, so the remaining pin, the 8th pin, is not connected. One important point that we should observe in this figure is the following. The inputs, the non-inverting input as well as the inverting input, are basically base terminals of transistors Q1 and Q2, and therefore the input current that we see, either that current or that current, is a base current of BJT. And since base currents are small, they are smaller than the collector currents by a factor of beta. We often say that these input currents for an op amp are negligibly small, and in other words, we can say that there is a large input resistance between the input terminals of the op amp. So this is a very important point to note, and when we analyze circuits, we will surely make use of this observation. Let us now look at the power supply connections to the op amp. Let's say, for example, this is 10 volts, this is also 10 volts. The negative terminal of this supply and the positive terminal of this supply are connected together, and that serves as the common ground. If you recall, there is no ground pin as such in the op amp, and if we say that the output voltage is, say, 2.5 volts, what we mean is it is 2.5 with respect to this common ground, and that is the same as this ground or this ground shown in these circuits. In our example, both of these are 10 volts, so this node VCC is at plus 10 volts with respect to ground, and this node minus VEE is at minus 10 volts with respect to the same ground. So that is how the power supply connections are made. Now let us look at the equivalent circuit of the op amp when it is operating in the linear region, and we will look at what we mean by linear region very soon. So here is the equivalent circuit, and you notice that its simplicity is really striking as compared to the internal circuit of the op amp that we saw in the last slide. All we have is three components: this resistance, this voltage controlled voltage source, and this other resistance. This is the input resistance connected between the non-inverting and inverting inputs of the op-amp, these two. This is AV times VI. If that is VI, this is AV times VI, where AV is the gain of the op-amp, it's so-called open loop gain of the op-amp, and RO is the output resistance of the op-amp. And the output voltage is taken between out and ground, that is between this node and this common node here. The equivalent circuit of the op-amp can be further simplified because this input resistance is generally a large resistance and this output resistance is a small resistance. So let's say this is very large, ideally infinite, and then we don't have the resistance here, we just have an open circuit. And let's say this is small, ideally 0, and then we don't have a resistance here, just a short circuit. And this equivalent circuit is often used, and it does explain very well the operation of most of the op-amp circuits. Let us make a few points. First, the external resistances that we're going to connect outside the op-amp are of the order of a few kilo ohms, and they are generally much larger than RO, the output resistance here of the op-amp, and much smaller than Ri, the input resistance of the op-amp. And therefore, with respect to these external resistances, we can assume that Ri is infinity and Ro is 0. And we can do that without significantly affecting the analysis. And that is what we have shown over here. Ri is infinity and Ro is 0. Second point, VCC and minus VEE are in the range plus minus 5 volts to plus minus 15 volts. So for example, if VCC is plus 5, then minus VEE is minus 5. And these connections must be supplied. That means we must connect this VCC pin of the op-amp to this supply here, and the minus VEE pin of the op-amp to this supply here. An op-amp will not work without them. So if you go to an electronics lab, hook up an op-amp circuit and forget to make these connections, then you will not see the output voltage that you would expect. When we draw op-amp circuits, the supply voltages are often not shown explicitly. That means we are not going to show these VCC and minus VEE pins of the op-amp in a circuit diagram, and we are also not going to show these voltage supplies. But it is of course understood that the VCC and minus VEE pins are actually connected to suitable voltage sources. Here is a table showing the parameter values for the 741 op-amp. The voltage gain, this gain here, ideally infinite. For the 741, it is 10 raised to 5 or 100,000, which is still a large number. And in terms of decibels, it is 100 dB. Ri, the input resistance, ideally infinite. For the 741, it is 2 mega ohms. And as we commented, this is still much larger than typical external resistance values, which are in the kilo ohms range. Output resistance RO, that one, ideally 0. For the 741, it is 75 ohms. And again, as we said, it is much smaller than the external resistances. We will now look at the VO versus VI relationship for an op-amp. VO is the output voltage with respect to ground, and VI is V plus minus V minus, this difference here. This figure shows the VO versus VI relationship. And as we can see, there are two distinct regions. One is a linear region, and the rest, that and that together, we will call as the saturation region. In the linear region, the output voltage varies linearly with the input voltage, V plus minus V minus, and the slope is the voltage gain of the op amp, often called the open loop gain of the op amp. And as we have seen, this open loop gain is a large number, 100,000. And let us see what the implications of that are. Now this relationship is valid only up to a certain point, and at that point the output voltage saturates either to a positive value or to a negative value. The positive value we will denote by Vsat, sat for saturation, and the negative value by minus Vsat. Typically, Vsat is something like 1.5 volts less than Vcc. For example, if Vcc is 15, then Vsat would be 13.5 volts. So then this limit would be plus 13.5 and this limit would be minus 13.5. In our example, we have taken Vsat to be plus 10 volts and minus Vsat to be minus 10 volts. Now this difference therefore is 20 volts, and we know the slope of this linear region, that is 100,000 or 10 raised to 5, and therefore we can calculate the width of this linear region. What would that be? That would be 20 divided by the slope, which is 10 raised to 5. So that comes to 200 microvolts, or the same as 0.2 millivolts. So that means this entire width is only 0.2 millivolts in this case. So that is going from minus 0.1 millivolt to plus 0.1 millivolt. So notice that these voltages are very small. 0.1 millivolt is 0.0001 volt. And these scales definitely are far apart, the X and Y. These are volts, these are millivolts. And if we plot this VO versus VI relationship using similar scales for the X and Y, then we will see something like this. So here the input voltage is going from minus 5 to plus 5. The output voltage is going from minus 10 to plus 10. And this entire region now looks like this. So it has got compressed, and you really can't see the width of this region in this figure. And that brings us to a very important point. For minus Vsat less than VO less than Vsat, that is this range here, Vi, which is V plus minus V minus, is VO divided by AV, and because AV is such a large number, Vi is very small, and we have already seen that Vi is in the range minus 0.1 millivolt to plus 0.1 millivolt. In other words, V plus minus V minus is nearly 0, and therefore V plus and V minus are virtually the same. So this is a very important observation, and we will make use of this when we look at op-amp circuits. Here is the VO versus VI relationship for an op-amp. Once again, there is this linear region which is very narrow, something like 0.2 millivolts or thereabouts. Then there is the saturation region which covers this part as well as this part. On the positive side, the output voltage saturates at plus Vsat. On the negative side, it saturates at minus Vsat. Now broadly, op-amp circuits can be divided into two categories. Op-amp operating in the linear region, one category. Op-amp operating in the saturation region, second category. And in this course, we will have a chance to look at both types of circuits as we proceed. Now, whether an op-amp in a given circuit will operate in linear or saturation region depends on these two factors. One, the input voltage magnitude, and second, the type of feedback. At this stage, we don't know what this means exactly, but there are two types of feedback, negative and positive, and we will take a qualitative look at feedback later. We start with op-amp circuits in the linear region. In the linear region, that means the op-amp is operating somewhere here. What can we say? The output voltage is AV times V plus minus V minus. That is the input voltage V plus minus V minus. And since AV is very large and VO is limited to this range, this V plus minus V minus, which is VO divided by AV, is very small. And of course, we have seen that earlier already. And in fact, in this graph, it appears like 0. So in other words, V plus and V minus are nearly the same. That's one observation. Second, since Ri is typically much larger than other resistances in the circuit, we can treat this as an infinite resistance or an open circuit. And then what it means is that this current is 0. If there is an open circuit here, this current is 0, this current is also 0. So the input current of the op-amp then is approximately 0. So for all practical purposes, we can ignore it. So these two are like our golden rules, and they will enable us to understand several op-amp circuits in which the op-amp operates in the linear region. So let's summarize once again. V plus and V minus are nearly the same, virtually the same, and the input current of the op-amp is 0. To conclude, we have seen the internal circuit of a typical op-amp and its VO versus VI relationship. We have also seen that although an op-amp is a very complex circuit, its nearly ideal behavior can make circuit analysis easy. In the next few classes, we will look at several op-amp circuits. So see you next time.